Hi again, welcome to the next video in the function series. In this video we review the two main techniques of transforming functions. Transformation is important when we need to take a basic curve and change it to another form so that it fits a particular situation. We might, for example, be describing the heights of people in a given locality, or explaining the number of infections from a virus over time, and so on. In short, transformations help us fit maths to the nature of the real world. When we graph functions, there is often a need to modify the basic structure of the equation to accommodate changes in location, conditions, etc. After all, mathematics is the way we try to explain all actions, behaviours, trends and interactions, human and mechanical. Hence we need to understand how to affect changes in basic functions, such as in lines, parabolas, hyperbolas, etc., when we try to model different circumstances and conditions. Don't complicate things. At this stage we need only two basic kinds of transformations for our functions and relationships. First, we need shifts, where we take the graph of a function and move the whole graph up or down or sideways. Secondly, we need dilations or enlargements, where we stretch the graph of a function vertically or horizontally without changing its central point. For a vertical shift, if we have a function fx and we add a constant, let's say 1, to every value, the effect is simply to move the graph up by 1 unit. The transformation can then be written as y is equal to fx plus 1. Simple. If we subtract a constant, say 2, from every y value, the effect is to move the graph down by 2 units, and our new function is y equals fx minus 2. Writing this strategy mathematically, we can say y is equal to fx plus v, where v is the vertical shift. When v is positive, then the curve moves vertically upwards. When v is negative, the curve moves vertically downwards. By way of example, y equals x plus 3 is really the line y equals x moved up 3 units. If we have y equals 1 over x minus 2, then that's the hyperbola y equals 1 over x moved down 2 units. So think, the y values change by the amount v for a vertical shift. In keeping with the strategy to be used for the other transformations, we view this transformation as replacing the y value with y minus v. So y equals fx becomes y minus v is equal to fx, which results in y is equal to fx plus v. But we're going to write the v on the left-hand side rather than the right-hand side. The situation for the horizontal shift is pretty much the same. Here we replace the x with x minus h to move the curve horizontally to the right. So the x in y equals fx is replaced and the function becomes y equals f x minus h. If h is positive, the curve moves to the right. If h is negative, the curve moves to the left. So for example, if we have the parabola y equals x squared and we replace the x with x minus 2, then the new parabola is y equals x minus 2 all squared, and it is shifted 2 units to the right, as you can see in this graph. For a horizontal shift, the x values are changed by adding or subtracting the amount h. So fx becomes fx minus h. For the second kind of transformation, we're talking about dilation. Now, dilation is often used to indicate that something is expanding. It is commonly used to describe the enlargement of the eye's pupil during an eye examination, where you get those drops in and then you can't see for a while. And sometimes it's used in other contexts as well. In mathematics, dilation describes a curve expanding away from an axis without changing the centre of the curve. Stretching the curve vertically is often referred to as vertical dilation. So vertical dilation is when the curve moves away from or closer to the x-axis. Horizontal dilation is when the curve moves away from or closer to the y-axis. We describe the extent of dilation by using a dilation factor. This factor is the multiplicative amount for the distance by which a point changes its position. So a dilation factor of 2 means the point changes to a location twice as far from the centre as it was originally. A dilation factor of 1/4 means that the point changes to a location 1/4 as far from the centre as it was originally. To stretch a curve vertically, we replace y in y equals fx with y over v. So y equals fx becomes y over v equals fx, so y is equal to v times fx. When v is greater than 1, the new value for y is v times the original value, so the curve is stretched up vertically. When v is between 0 and 1, 1 over v is very much less than the original value, so the curve is shrunk vertically. When v is less than 0, the curve changes in size by the v factor, but it is also flipped around the x-axis. v equals -1 is a straight reflection about the x-axis. Example. If we have y equals x squared, and we can look at the transformations by firstly having a dilation or expansion factor of 3, and we write this underneath the y. So we've got y over 3 equals x squared. Clearing the fraction, we have y is equal to 3x squared. So the dilation factor of 3 makes the y value larger, and so it's further from the x-axis. If, however, we have 3y is equal to x squared, then the dilation factor is now 1/3, because it's y divided by 1/3 is equal to x squared. Clearing that, we have y is equal to x squared over 3. Consequently, the y values decrease, and we can see this from the diagram. The middle curve is y equals x squared, so that's our standard. If we have the dilation factor of 3, in other words, it's y over 3, or the y equals 3x squared curve, that's dilated or extended the curve vertically by a long way. If we have the dilation factor of 1/3, then that becomes the red curve. We have pulled the values for y down through that factor. For horizontal dilation, we replace the x in f of x with x over h. So if y is equal to fx, with a horizontal dilation, we write y is equal to f of x over h, with h being the dilation factor. When h is greater than 1, the new value for x is h times the original value, so the curve is stretched horizontally. If h is between 0 and 1, then 1 over h is less than the original value, so the curve is shrunk horizontally. When h is less than 0, the curve changes in size by the h factor, but it's also flipped around the y-axis. h equals -1 is actually a reflection about the y-axis. Example, we have y is equal to the absolute value of x, and we're going to draw two transformations. The first one is using a dilation factor of 2, and so it's going to affect the x term, so we write y is equal to the absolute value of x over 2, because the dilation factor is 2. So horizontally, all the x values changed by a factor of 2. If, however, we wrote the absolute value of 2x, then putting that in the normal form, we can have the absolute value of x divided by 1/2. So the dilation factor is 1/2. and so that's going to reduce all the values of x by a factor of 2. We can see these effects in the graph that I've got in the bottom right. We can see the middle lines are y is equal to the absolute value of x. If we have y equals x over 2, which are the bottom green lines, then they've been flattened out a lot, and so they've been enlarged or dilated horizontally, whereas in contrast, the top blue lines, y equals absolute value of 2x, have been brought back right in much closer to the y-axis. We can bring all of these ideas together in a fairly topical example that so many people are talking about, that is, flattening the curve. Suppose we are talking about a virus outbreak in a small country region. We know that the distribution of treatment will approximately follow a parabola. We know that from our experience, say. We also know that there are only 15 beds available. Our health policies can delay the onset of the virus, but not stop it. So we draw our typical upside down parabola, y equals minus x squared, to describe the spread of the virus. We want to spread out the number of days across which this virus is going to take effect, and so we use a horizontal dilation of 3, and that's going to widen the curve out. We also want to say that we're going to vertical shift it by 30 so that we can make the maximum value equal to the number of daily infections which we're expecting. Now take that curve, because part of the curve has got negative days and we only can have positive days, of course, and so we're going to shift it across 25 days so that the maximum of 30 cases is going to occur at 25 days. And so we've got an x minus 25 to allow us to move that horizontally. We're now going to adopt several health strategies to help us fight the virus. The first thing we're going to do is to delay the peak number of cases on a daily basis until day 35. So we're going to change our 25 to a 35 as our horizontal shift, and then we're going to dilate the curve horizontally even further and change our dilation factor of 3 to a dilation factor of 9. So that's going to flatten the curve right down, but it would still, if we didn't change anything, allow a maximum number of infections which was too high. So we change our vertical shift to 10, so it's y minus 10 actually, and that'll give us a maximum infection rate of 10, which is fine because we've only got 15 hospital beds. The effect of all of that is that we're going to spread out the virus to accommodate all the expected cases, starting at around about day 6 and ending at about day 64. So we've been able to accommodate the virus within our limitations, but over a longer period. Just a couple of quick things before we go. It's easier to do dilation effects first, and then you do your shifting, because you can get mixed up in terms of what it is that you're doing. If you're only doing shifting, then you can do vertical and horizontal shifts in any order. It doesn't matter, they commute. If you're doing 2 dilations, they also commute, so you can do the 2 dilations in any order and you're not going to have a problem. You can also do a shift in one direction and a dilation in the other, as long as one is vertical and one is horizontal, and you're not going to have a problem. Secondly, if you're given a problem and you've been asked to identify what transformations have been used, what you should do is to manipulate the terms, just like changing the subject of an equation, and put them into a standard form. So you've got the y minus something on one side and your x minus something over a dilation factor on the other. Just a whole lot easier. I've also included a table which is going to take you a little while to read, but I'm just putting it here for completeness, which gives you the vertical and horizontal actions that you're going to take and the interpretations for shifts and then for dilations. Now you don't have to worry too much about that table, just recognise it's here because it's also reported again on the website drjaysmath.com. So have a look at it there and you can easily print it off if you wanted to. So that is the story of transforming functions and relationships. Shifting and dilation are the two basic types of transformation, and they take us a long way in our analyses. Thanks for watching this video. Go and do some transformation questions in Test Yourself 1 on my website at drjaysmath.com. Good luck. See you in another functions video.